share the content with you. Now you should be able to see the slides, I think. Okay. First, we will talk about traversal of the trees. Usually, we have to go through all the nodes in the tree, but in some specific order. And this type of traversal is like walking through the tree, and during this walk we get to each node one by one and process these nodes in a sense, right? We call this walk as tree traversal. There are several kinds of tree traversals. We are going to talk about 3 specific traversals in this course. Remember the recursive definition of the tree. Tree could be empty, or tree, especially these traversals are for binary trees. So I should say binary tree traversals. And remember the definition of binary trees in recursive definition. It could be empty, or the binary tree has a root node and 2 subtrees, left subtree and right subtree, right? Left subtree and right subtree, 2 subtrees for the binary tree. And these 3 different traversals specifies how we traverse these 3 components: left subtree, root node, and the right subtree. There are 3 components, and the order of these, traversal order of these, or visit order of these 3 components will determine the traversal type. In pre-order traversal, we first traverse or process the root node, then these 2 left and right subtrees later on. In post-order traversal, we process left subtree and right subtree first the subtrees, then the root node. And in order traversal, we process left subtree, all the nodes in the left subtree, then the root node, then we process the right subtree. How we are going to process left or right subtrees? Of course, recursively, since the recursive definition is provided, right? Based on this recursive definition, this is a tree, right? How we process the whole tree should be same as how we process the left subtree or right subtree, right? This is a recursive method. So the method is simple. As I said, in pre-order we visit the root node, then the left and right subtrees. In order traversal, we traverse the left subtree, then the root node, then the right subtree. In post-order traversal, we first traverse the left and right subtrees, then the root node. Here we see the algorithms as well.
So
As I said,
I just see your first slide. I mean,
doesn't
I
change.
think I just see three
Yeah,
traversals right now. Is it correct?
I'm at the second slide right now. Everybody sees the first slide, or just you? Is there anybody can see the second slide?
We are in the second slide.
Yes, yeah, you can see it. So that there should be some problem in your client side.
Okay.
Probably you should log out and log in again.
Okay. Thank you.
Okay, these are the algorithms for three different traversal types. As you see, for all of them, having an empty tree is the base case. If the tree is empty, we don't have anything to do. Nothing needs to be traversed, right? Otherwise, in pre-order traversal, first we visit the root node. Visiting root node means processing the root node. However, we need to process, for example, we may need to build a string, write them on the screen, or probably add the values that are in the nodes, and anything you need to do about the root node has to be done here first. Then recursively we process the left subtree, then we process the right subtree in pre-order traversal. So we have two recursive calls at each algorithm, and in the pre-order traversal algorithm, we process the left and right subtrees after visiting the node. And in order traversal, we process the root node in between two recursive calls to left and right subtrees. And in the post-order traversal, first we process the left and right subtrees, afterwards we process the root node. That's the only difference. So how we traverse the three components, root node, left subtree, and right subtree, the order of processing these three components is different in these three different tree traversals. This is another way to visualize these tree traversals. We can talk about Euler tour. In Euler tour, we start from the root and we keep the tree always on our left hand side. When we go like this, the tree is on our left hand side always. When we come to a leaf, we have to go around the leaf and keep the tree on our left hand side and go through all tree until we reach the root node again. This kind of tour is called Euler tour. As you see, each node is reached in this tour 3 times. First, when we go down to its subtrees, we come to this B and go down to its left subtree. So this down arrow signifies this visit. Next, after we finish traversing the left subtree, we go to right subtree to B, right? We see B again, and after traversing left subtree, we start traversing or processing right subtree. This second visit is signified by right arrow here. And the third time, after all subtrees are traversed, we go back up to the parent. This last visit is signified with the up arrow. So each node is actually visited 3 times. For example, this D is visited while going down to left subtree. There is no left subtree. Right away we go to right subtree, and after right subtree is reversed, we go up, right? Similarly here for E has left subtree, so after coming from the parent, we go through E and pass through left subtree. After we finish, we go to right subtree. Since it is empty, we just go up immediately, right away. So each node is traversed twice. For example, for this node, we come from F, down arrow, and since there is no left subtree, we go right, and since there is no right subtree, we go up immediately. So these 3 passes are one after the other right away, right? For the leaf nodes, of course. Is it clear? So we see we see each node 3 times in this Euler tour, and each pass actually signifies the one of these traversals. For example, if we process a node while going down, then we first process A, then B, then D, then G, and E, H. This is pre-order traversal. So if we process nodes when we see first on this down arrow, right? That is pre-order traversal. If we process each node during this right arrows after finishing the left and not processing the right, if we process it, this is in order traversal. As you see, when we go down, first right arrow will be for D, then G, then B, then H, then E, etc. This is in order traversal. And lastly, if we process them while going up, we have post-order traversal. Since we go down, right and down, and first time we go up is for G, then D, then H, E, B, etc. Right? And this is post-order traversal. So,
Sir,
yes.
can you repeat pre-order again? Pre-order traversal.
In this pre-order traversal, we process while going down. So first we process A, then go down to B and this down arrow, then D, down arrow, right down, G, up, down again, E, etc. So A, B, D, G, E, H, and so forth. This is pre-order traversal. Is it clear now?
Clear.
Okay. So this is how we traverse the trees. These three different traversals are possible for any binary tree. For some specific trees, these traversals give useful information. For example, for binary search trees, if you traverse the binary search tree in order traversal means traverse left subtree, then the root node, then the right subtree. And as you remember, the root node is greater than everything in the left subtree and less than everything in the right subtree, right? Since we traverse the left subtree first, then the root node, then the right subtree, of course, in order way of traversing left and right subtree should be performed. In that case, dog is in the middle, and here we have roof here since only one element, but while traversing this right subtree, left subtree, excuse me, we have cat as the root node, left subtree canine, and there is no right subtree, so left subtree is traversed first, canine, then root, cat, then right subtree. This is what we get when we traverse the binary search tree in order. And as you see, the values in order traversal is sorted. So canine is the smallest element, then cat, then dog, then wolf, right? So it is sorted order. We can use in-order traversal to get sorted order for binary search trees. That's specific to binary search trees, of course. From smallest to largest. Okay, we all know the expression trees, right? In expression trees, in-order traversal gives this value. Since we traverse this one, while traversing that one, we traverse x, then plus, then y, etc. Then multiplication and right subtree, right? We get this infix expression, but in this infix expression, the parentheses are not there. Parentheses should be put in correct positions, like these, right? And since we perform this addition first, like this, to get perfect infix expression. Remember, the postfix and prefix expressions doesn't include any parentheses, right? And they can be obtained by pre-order and post-order traversals. For example, if you traverse the left subtree, right subtree, then the root node, which is post-order traversal, this is what we get from the left subtree, this is what we get from the right subtree, and the root node. As you see, we get a postfix expression. Similarly, if you traverse preorder, we get prefix expression, first the root node, then the last subtree, and the right subtree, right? For this right subtree, first root, then left subtree, and right subtree. Similarly, for this one, first root, then left subtree, then right subtree. Right? So, different traversals are important for different various trees. You may need to use all of them time to time. So it's better to know all of them. Okay, this is all for tree traversals. We didn't talk about the code since we don't know how to implement a binary tree yet. Now we are gonna talk about implementing binary tree by using a binary tree class. We are gonna talk about a binary tree class right now. Okay, to be able to implement a binary tree, there are several ways. One of the simplest way is to use node structure. A node have a field of that reference to data and two references to separate nodes, one for the left subtree, one for the right subtree. So as in linked list, we have just linear structure and we need to know only the next node. But here, tree is not linear and we have two links in binary tree, one for the left subtree, one for the right subtree, or right child and left child, right? So two references are required in binary tree implementation. One for the left child reference. Left child will be another node, of course. The other one is for the right child reference. That's another node, or could be null as well, right? So this is how we implement the node structure. It has the data, left reference and right reference. As you see, all of them are defined protected. Protected means then we have to use this class as superclass of, or if you would like to extend this class with another node structure, you can use it, right? And can access the values directly. And that's why we are gonna need to extend this class later on. That's why it is defined to be protected, not private. There is only one constructor which gets the data value and the left and right pointers out null. And we have toString method that converts the data in the node to this string. Okay, this is how the node structure is defined. And serializable. Do you know what serializable is? A serializable class. Actually, it is an interface. It doesn't have any method in it. So this node class doesn't need to implement any extra method, but it signifies that we can convert this to a binary file, save into a binary file, and read the data in the node from a binary file. We are gonna see the details later on in this class. You may know it beforehand, probably. So the node is there to be protected since it's gonna be used as a superclass. This is a node structure and how they are linked together to form a tree. Actually, we are going to talk about a binary tree. Binary tree will have node class as an init class. And in that binary tree, we will keep a root information only. That's the reference for the root node. And the root node gives true references for the left child. And we follow this to left child and for the right child. Similarly, each node has two children, left child and right child. And for this node, left and right are null, so there is no left child or right child. So it's a leaf node, right? So this is how we are going to organize the nodes to form a binary tree. We are going to define a binary tree class. It's a generic class. And this is of type binary tree. Then if bt is the variable that gives the reference of this binary tree, then bt.root is the value here, a reference of the root node. bt.root data is the data value here, which could be a star symbol, right? A star character. Or bt.root left is the reference of this node, right? bt.root right is the reference of the right child of the root node. And if we have to access a data element of the right child, we can use this, right? Okay, this is the declaration of the data fields and the methods in the binary tree class. There is only one data field in the binary tree class, which is for the root value, a node reference. As I said, the binary tree class has an inner class node, right? There are three constructors for the binary tree. One of them is no parameter constructor, public constructor, which constructs a empty binary tree. The second constructor is one parameter constructor. As you see, it takes a node reference as a parameter, root node as a parameter. So it constructs a tree with one node, with the root node. So this node will be, the node provided will be the root node of the binary tree. But since it gets a node reference, which is an internal inner class type, right? It cannot be public. It is protected. So it can be used by other classes that extends this binary tree, but other classes cannot use this protected constructor. Here we have another constructor, three-parameter constructor. We specify the value at the root and two binary trees, left subtree and right subtree. We combine this left subtree and right subtree together and connect them to a root node that contains the data value given as a parameter. So it will not copy the trees, but just link them together by using a root node to form a new tree. Okay. We have some accessor methods to get to access the left subtree or right subtree or data. These are three simple methods that returns the roots left or right or data references, right? As you see, to be able to return from this, it should return a binary tree. It cannot return the roots left directly, since root left has type node, right? We cannot return the node, but we will construct a binary tree using the roots left, and the binary tree constructed will be returned by get left subtree and get right subtree methods. Both returns a binary tree. But here, for this get data method, we can return root data directly, right? To be able to check whether the node is leaf or not, we can check whether the right subtree and left subtree are empty, right? There's simple method that returns a Boolean value. ToString method will return a string which contains the values in the data in the tree in specific way, right? To be able to implement this ToString method, we will use this pre-order traversal method, which is private, as you see. This pre-order traversal method is a recursive method, as you remember, pre-order traversal. That starts from the root node, and it will use some depth value to print this tree in the string nicely. And it will use a string builder to put the values in the string builder, and later on in this string method, the string is formed and returned, right? So only value that is updated and recursion used to stop recursion is the node. The others are also updated, but they are not going to be used to stop the recursion. Last method, read binary tree method, takes a scanner as a parameter and reads the values in that scanner. You scan through the values there and forms a binary tree. Of course, the values that is scanned through by the scanner should be formed in a special way, and we will assume that that scanner is formed by string method. So this is the declaration of the binary tree class. As you see, it's a generic class, and it has actually, first of all, it has an inner class called node, and it keeps a reference to root node in the binary tree, and it's serializable again. What do we mean by serializable? Serializable interface doesn't have any method, but it is an indicator that the class can be written to a binary file using object output stream, or can be read from a binary file using object input stream. So that is just an indicator, doesn't have any method, so you don't need to do anything to be able to read and write into a binary file. Java provides the functionality for you. Java has a class object output stream and object input stream. Object output stream is to write the object in a binary file, but these objects has to be serializable. If we declare object as serializable, as in here, implement serializable, these objects can be written onto object output stream. Now, this is an example way of doing it. You can create an object output stream by specifying the file name and creating file output stream as a parameter. Out is the object output stream we have created. Now, if we say write object and give the object to be written, Java prints that object, and actually it performs a deep copy. It traverses all the references and copy the values at that references and the references in there. It performs a deep copy. So the whole binary tree will be copied into the file if you perform write object, if you call write object method for a binary tree object. Okay, so it is easy to write using this two lines in a binary file. Of course, it's better to use these two lines in try-catch structure to catch the exceptions. To be able to read the file in, again, we create a file input stream, and out of it we create object input stream, and we just need to say read object. Read object will return an object class instance, and we can downcast it to correct object class easily, right? Of course, if there is a problem in reading or downcasting, we will get an exception. That's why we need to put them into try-catch block. Okay, in using this object output stream and object input stream, you should be careful. If you compile your source code, the classes will have different IDs, and since the classes changed, Java doesn't let you to read again. So after writing it, you shouldn't recompile the source code before reading them back in. Okay, so signatures will not match, and you will get an exception while reading the object. Otherwise, okay. After this simple introduction about serializable thing, remember this. We are talking about binary tree class. It keeps the root node, and we would like to implement these methods and these constructors, right? Here are the implementations. Simple if no parameter constructor, we just make the root node null. In one parameter constructor, we make the root node to point to have the value specified as a parameter. Of course, both are roots. We have to use this root, right? Use this. This is the three parameter constructors. In here, we have to create. We have supplied two trees, right? Left tree and right tree. We can access to their root nodes by left tree root and right tree root easily. And to be able to form a tree from these left and right subtrees, we have to create a root node, is in here, by supplying the data provided to the method, right? So we create a root node assigned into the root, so it is root node now. And the left subtree should be pointing to the left tree's root, and right subtree pointing to right tree of the root. But we have to be careful. If the left tree is null, root left should be null as well. We cannot access to root node of the left tree if left tree is null. We check whether left tree is null or not and perform the operation. Similarly for the right tree. So after this, we have a complete tree, right? Containing both left subtree, right subtree, and the data at the root. Okay, how long does it take to construct not empty tree? Constant time, right? Constructing a binary tree with specifying the root node, it takes constant time. Similarly, this tree parameter constructor is again constant time operation, right? Since everything here is constant time operations. There is no complicated operation here. Everything is constant time. Now, to get the left subtree, we cannot, as I said, we cannot return root left right away since the type of the root left is node. We convert it to a binary tree by constructing a new binary tree, right? Using one parameter constructor. Of course, before doing that, we have to make sure that the tree is not empty and a left subtree is available or not. If the root is empty or left subtree is not available, you just return null. Otherwise, you create a binary tree and return. For the get right subtree, it is very similar. Again, this method is constant time, right? Is leaf, it is another constant time operation since we can check whether left and right are null or not. But we should be careful while calling this leaf. There should be a root node. Having a root node is not checked here, as you see. So you should be careful. Okay, so string method. So string method will convert the tree into a string. We will use string builder. Why? Why don't we use, without using string builder, we can concatenate strings together to form a string, right? Why do we use string builder? Because efficiency, right? Since by using string builder, we can put several strings in a way without putting them together. Adding something into string builder is constant time, but concatenating two strings may not be constant time, right? And at the end, we convert the string builder into a string just once. We put them together. We put all the strings in string builder together in just once. Of course, this last line will not be constant time, but it will depend on the total size of the string. Right? How we will create this string builder, how we put the tree into string builder, we will use this pre-order traversal to perform that. Okay, before going further, let's have a break. And after the break, we will talk about how we perform this pre-order traversal. Okay, let's have a break for 10 minutes.
Sure. Can I ask a question?
Yes.
By saying string builder, I didn't understand exactly what do we do. Do we use the methods of it here?
In string builder is a class defined in Java, and we use that string builder in this method. And why do we use? Because of the performance of the string builder. String builder doesn't concatenate strings while we are adding them together. Here we are gonna append new strings into string builder. Then we append a new string. String builder doesn't concatenate them together in its internal structure. Just put these strings in a list probably, and afterwards, when we convert to string, put all the strings together just once, at once. And the performance is better if you do that. Otherwise, you can, instead of this append, you can keep a string and concatenate the new string onto a previously built string each time, and it will take a lot of time. We have seen that in toString method of the linked list, right? Do you remember the string method of the linked list? Let's
Yes.
let's talk about it after the break. Okay, let me find that. Let me find that code and talk about it on that code as well after the break.